In mathematics, the repeating decimal 0.999 or denotes a real number that can be shown to be the number 1. In other words, the symbol 0.999 and 1 represent the same number. Proofs of this equality have been formulated with varying degrees of mathematical rigor, taking into account preferred development of the real numbers, background assumptions, historical context, and target audience. Every nonzero, terminating decimal has an equal twin representation with infinitely many trailing nines. The terminating decimal representation is usually preferred, contributing to the misconception that it is the only representation. The same phenomenon occurs in all other bases or in any similar representation of the real numbers. The equality of 0.999 and 1 is closely related to the absence of non-zero infinitesimals in the real number system, the most commonly used system in mathematical analysis. Some alternative number systems, such as the hyperreals, do contain non-zero infinitesimals. In most such number systems, the standard interpretation of the expression 0.999 makes it equal to 1, but in some of these number systems, the symbol 0.999 admits other interpretations that contain infinitely many nines while falling infinitesimally short of 1. The equality 0.999 equals 1 has long been accepted by mathematicians and is part of general mathematical education. Nonetheless, some students find it sufficiently counterintuitive that they question or reject it. Such skepticism is common enough that the difficulty of convincing them of the validity of this identity has been the subject of several studies in mathematics education. Algebraic proofs showing that 0.999 represents the number 1 use concepts such as fractions, long division, and digit manipulation to build transformations preserving equality from 0.999 to 1. However, these proofs are not rigorous as they do not include a careful analytic definition of 0.999 equals fractions and long division equals. One reason that infinite decimals are a necessary extension of finite decimals is to represent fractions. Using long division, a simple division of integers like 1 and 9 becomes a recurring decimal, 0.111, in which the digits repeat without end. This decimal yields a quick proof of 0.999 equals 1. Multiplication of 9 times 1 produces 9 in each digit, so 9 0.111 equals 0.999. And 9 1 and 9 equals 1, so 0.999 equals 1. This result is consistent with other ninth fractions, all of which have repeating decimals, such as 3/9 and 8/9. If 0.999 is to be consistent, it must equal 9/9 equals 1. Equals digit manipulation equals, when a number in decimal notation is multiplied by 10, the digits do not change but each digit moves one place to the left. Thus 10 0.999 equals 9.999, which is 9 greater than the original number. To see this, consider that in subtracting 0.999 from 9.999, each of the digits after the decimal separator cancels, that is the result is 9 and 9 equals 0 for each such digit. Equals discussion equals, although these proofs demonstrate that 0.999 equals 1, the extent to which they explain the equation depends on the audience. In introductory arithmetic, such proofs help explain why 0.999 equals 1 but 0.333 n. If and are two Cauchy sequences, then they are defined to be equal as real numbers if the sequence has the limit 0. Truncations of the decimal number BO B1 B2 B3 generate a sequence of rationals which is Cauchy. This is taken to define the real value of the number. Thus in this formalism the task is to show that the sequence of rational numbers has the limit 0. Considering the nth term of the sequence, 4, it must therefore be shown that this limit is plain if one understands the definition of limit. So again 0.999 equals 1. The definition of real numbers as Cauchy sequences was first published separately by Eduard Heine and Georg Cantor, also in 1872. The above approach to decimal expansions, including the proof that 0.999 equals 1, closely follows Griffiths and Hilton's 1970 work A Comprehensive Textbook of Classical Mathematics, A Contemporary Interpretation. The book is written specifically to offer a second look at familiar concepts in a contemporary light. Infinite decimal representation equals. Commonly in secondary schools mathematics education, the real numbers are constructed by defining a number using an integer followed by a radix point and an infinite sequence written out as a string to represent the fractional part of any given real number. In this construction, the set of any combination of integers and digits after the decimal point is the set of real numbers. This construction can too be rigorously shown to satisfy all of the real axioms after defining an equivalence relation over the set that defines 1 equals x 0.999. As well as for any other non-zero decimals with only finitely many non-zero terms in the decimal string with its trailing nines version. With this construction of the reals, all proofs of the statement 1 equals 0.999 can be viewed as implicitly assuming the equality when any operations are performed on the real numbers. Generalizations, the result that 0.999 equals 1 generalizes readily in two ways. First, every non-zero number with a finite decimal notation has a counterpart with trailing nines. For example, 0.24999 equals 0.25, exactly as in the special case considered. These numbers are exactly the decimal fractions, and they are dense. Second, a comparable theorem applies in each radix or base. For example, in base 2 0.111 equals 1, and in base 3 0.222 equals 1. In general, any terminating base B expression has a counterpart with repeated trailing digits equal to BA1. Textbooks of real analysis are likely to skip the example of 0.999 and present one or both of these generalizations from the start. Alternative representations of 1 also occur in non-integer bases. For example, in the golden ratio base, the two standard representations are 1.000 and 0.101010, and there are infinitely many more representations that include adjacent ones. Generally, for almost all q between 1 and 2, there are uncountably many base q expansions of 1. On the other hand, there are still uncountably many q for which there is only one base q expansion of 1, other than the trivial 1.000. This result was first obtained by Paul Erdős, Miklos Horváth Th., and Istvan Joe cubed around 1990. In 1998 Vilmos Kmenich and Paolo Lority determined the smallest such base, the Kmenich-Lority constant q equals 1.7872311650, in this base, 1 equals 0.1101001010100010101010101011. The digits are given by the Thuy-More sequence, which does not repeat. A more far-reaching generalization addresses the most general positional numeral systems. They too have multiple representations, and in some sense the difficulties are even worse. For example, in the balanced ternary system, 1/2 equals 0.111 equals 1.111, in the reverse factorial number system, 1 equals 1.000 equals 0.1234 equals impossibility of unique representation equals, that all these different number systems suffer from multiple representations for some real numbers can be attributed to a fundamental difference between the real numbers as an ordered set and collections of infinite strings of symbols, ordered lexicographically. Indeed, the following two properties account for the difficulty: if an interval of the real numbers is partitioned into two non-empty parts L, R, such that every element of L is less than every element of R, then either L contains a largest element or R contains a smallest element, but not both. The collection of infinite strings of symbols taken from any finite alphabet, lexicographically ordered, can be partitioned into two non-empty parts L, R, such that every element of L is less than every element of R, while L contains a largest element and R contains a smallest element. Indeed, it suffices to take two finite prefixes P1, P2 of elements from the collection such that they differ only in their final symbol, for which symbol they have successive values, and take for L the set of all strings in the collection whose corresponding prefix is at most P1, and for other remainder, the strings in the collection whose corresponding prefix is at least P2. Then L has a largest element, starting with P1 and choosing the largest available symbol in all following positions, while R has a smallest element obtained by following P2 by the smallest symbol in all positions. The first point follows from basic properties of the real numbers. L has a supremum and R has an infimum, which are easily seen to be equal. Being a real number, it either lies in R or in L, but not both, since L and R are supposed to be disjoint. The second point generalizes the 0.999/1.000 pair obtained for P1 equals 0, P2 equals 1. In fact, one need not use the same alphabet for all positions or consider the full collection of possible strings. The only important points are that at each position a finite set of symbols can be chosen from, and that making a valid choice for any position should result in a valid infinite string. Under these assumptions, the above argument shows that an order-preserving map from the collection of strings to an interval of the real numbers cannot be a bijection. Either some numbers do not correspond to any string, or some of them correspond to more than one string. Marco Petkovic has proven that for any positional system that names all the real numbers, the set of reals with multiple representations is always dense. He calls the proof an instructive exercise in elementary point set topology. It involves viewing sets of positional values as stone spaces and noticing that their real representations are given by continuous functions. Applications: 1 application of 0.999. As a representation of 1 occurs in elementary number theory. In 1802, H. Goodwin published an observation on the appearance of nines in the repeating decimal representations of fractions whose denominators are certain prime numbers. Examples include 1/7 equals 0.14285714287, and 142 plus 857 equals 999. 1/73 equals 0.0136986301369863, and 0136 plus 9863 equals 9999. 1/77 equals 0.01298701297, and 0129 plus 870 equals 999. E. Maidi proved a general result about such fractions, now called Maidi's theorem, in 1836. The publication was obscure, and it is unclear if his proof directly involved 0.999. But at least one modern proof by W. G. Lavitt does. If it can be proved that a decimal of the form 0 B1 B2 B3 is a positive integer, then it must be 0.999, which is then the source of the nines in the theorem. Investigations in this direction can motivate such concepts as greatest common divisors, modular arithmetic, Fermat primes, order of group elements, and quadratic reciprocity. Returning to real analysis, the base 3 analog 0.222 equals 1 plays a key role in a characterization of one of the simplest fractals, the middle thirds Cantor set. A point in the unit interval lies in the Cantor set if and only if it can be represented in ternary using only the digits 0 and 2. The nth digit of the representation reflects the position of the point in the nth stage of the construction. For example, the point 2 or 3 is given the usual representation of 0.2 or 0.2000, since it lies to the right of the first deletion and to the left of every deletion thereafter. The point 1 or 3 is represented not as 0.1 but as 0.0222, since it lies to the left of the first deletion and to the right of every deletion thereafter. Repeating nines also turn up in yet another of Georg Cantor's works. They must be taken into account to construct a valid proof, applying his 1891 diagonal argument to decimal expansions, of the uncountability of the unit interval. Such a proof needs to be able to declare certain pairs of real numbers to be different based on their decimal expansions, so one needs to avoid pairs like 0.2 and 0.1999. A simple method represents all numbers with non-terminating expansions. The opposite method rules out repeating nines. A variant that may be closer to Cantor's original argument actually uses base 2, and by turning base 3 expansions into base 2 expansions, one can prove the uncountability of the Cantor set as well. Skepticism in education. Students of mathematics often reject the equality of 0.999 and 1, for reasons ranging from their disparate appearance to deep misgivings over the limit concept and disagreements over the nature of infinitesimals. There are many common contributing factors to the confusion. Students are often mentally committed to the notion that a number can be represented in one and only one way by a decimal. Seeing two manifestly different decimals representing the same number appears to be a paradox, which is amplified by the appearance of the seemingly well-understood number 1. Some students interpret 0.999 as a large but finite string of nines, possibly with a variable, unspecified length. If they accept an infinite string of nines, they may still expect a last 9 at infinity. Intuition and ambiguous teaching led students to think of the limit of a sequence as a kind of infinite process rather than a fixed value, since a sequence need not reach its limit. Where students accept the difference between a sequence of numbers and its limit, they might read 0.999 as meaning the sequence rather than its limit. These ideas are mistaken in the context of the standard real numbers, although some may be valid in other number systems either invented for their general mathematical utility or as instructive counterexamples to better understand 0.999. Many of these explanations were found by David Tall, who has studied characteristics of teaching and cognition that lead to some of the misunderstandings he has encountered in his college students. Interviewing his students to determine why the vast majority initially rejected the equality, he found that students continued to conceive of 0.999 as a sequence of numbers getting closer and closer to 1 and not a fixed value, because you haven't specified how many places there are or it is the nearest possible decimal below 1 foot. Of the elementary proofs, multiplying 0.333 equals 1 a 3 by 3 is apparently a successful strategy for convincing reluctant students that 0.999 equals 1. Still, when confronted with a conflict between their belief of the first equation and their disbelief of the second, some students either begin to disbelieve the first equation or simply become frustrated. Nor are more sophisticated methods foolproof. Students who are fully capable of applying rigorous definitions may still fall back on intuitive images when they are surprised by a result in advanced mathematics, including 0.999. For example, one real analysis student was able to prove that 0.333 equals 1 a 3 using a supremum definition, but then insisted that 0.999